Okay, so today we're starting to learn about magnetic field, and you all learn about, about the magnet. And you all know that there are such things as a permanent magnet. And you know that magnets have two poles that like poles, north and north, they repel. North and south, they attract. And there is a thing that's called compass, which has north and south pole. By the way, the proper name is north and south pole. The full name is north-seeking and south-seeking pole. Why is that? We will talk a little bit later. But so we have permanent magnets. What's creating those magnetic properties? What makes magnet a magnet? To answer this question, let's consider next thing. We take the coil, and we will connect it to the current. So it does not show any magnetic property, so it does not affect the wood compass next to the coil, no effect on it. Shows that there is no effect on the compass. There is no current. There is no current in the coil. Now we will make a current.
I don't know what do you want me to do? Okay.
Now we will make current through the coil, and this one is non-magnet. As you can see, it's not affecting the compass at all. Not affecting compass. But now I will put some current through the wire. And I will turn the current on, and with the compass showing one direction. I turn current on, and it changed. So what's wrong with this one? Yep. So it's current on, current off. You see, when current on, we have the compass turning. So what conclusion we can make? What's creating the magnetic field? Now we'll put it for some time here. Then I will later on need assistance again. What creating magnetic field? Current. When we put current in, we had a magnetic field created. But what's created current in the permanent magnet? What's creating current in the permanent magnet? What current is in the permanent magnet? What is the current in the permanent magnet? What all matter made from? What all matter made from? Atoms. What atoms made from? Electrons and nucleus. And what electron doing in atom all the time? They're moving, and this is what is electric current? Movement of the charges. So electrons moving in the atom around the nucleus, they create magnetic field. So magnetic field is created always by electric current. Not always, there is one case when it can be created without moving charges, but moving charges create magnetic field. Then why only certain material demonstrate can become permanent magnets? Because magnetic field, now let's talk about direction of the magnetic field. If we have magnet, permanent magnet, we have north pole and south pole. and we saying that direction, remember with electric field, what we choose as direction of electric field?
Opposite of force.
What we choose as direction of the electric field?
Positive.
Force acting on
Electron. Positive.
positive charge. In the magnetic field, we check in the direction, if you take the compass, the small magnet that can freely rotate, and we put it into this point, that's where the north pole of that magnet will be pointing. And because north and north repel, north and south attract, which direction compass will be pointing? And here. Which direction compass will be pointing? It has no, with its north pole. North and north repel. So it will be pointing away. So direction, we take as direction of magnetic field, is direction in which compass will pointing if you will place it in that field. So that will be direction of the magnetic field. That is the direction of the magnetic field. That is direction of magnetic field. So, because north pole of the compass, and complete name is north seeking pole. North seeking pole. The pole that pointing seek north. It's away, will be away. Does it make sense why it's away from north? We take this as direction. Now there is some difference between the lines of electric and magnetic field. Remember, in electric field we had, when we had two charges, let's say positive, negative, we had electric lines start on the positive, finish on the negative. They had beginning, they had end. By the way, we will later discuss there is a case when it can be no beginning and end, when they will be closed, but when we have charges, they are closed. Lines of magnetic field, they always close. They never have beginning or end. They always close. So they're going through the magnet. And if you draw another line, it will go, it always must be closed. Going through the magnet, lines of magnetic field always close. They don't have beginning, don't have end. Lines of magnetic field. And so as we established, that magnetic field created by the current, and it could be movement of the electrons in the atom, but it could be that one electron creates magnetic field directed this way, another electron created magnetic field pointed this way, another way. So overall magnetic field of the atom will be zero. And that's what happens with many materials. Only in some materials, like iron, some other, the atom has overall magnetic field. They not cancel, because each electron, each single electron creates magnetic field. But overall magnetic field of the material, of the atom or material, can be zero. But in some materials, the magnetic field of atom is not zero. Plus, the magnetic fields of the neighboring atoms, they can align. But if we have, let's say, a piece of metal, which is non-magnetic, as you can see, it's not magnetic. But if I now put magnet to it, and this becomes magnetized as well, because it holds another piece of metal, which is, if I remove from the magnet, they're not magnetized. By the way, how we, so get back to this. Then if you have piece of, let's say, iron, it has areas, they call domains, in which in each of those areas, magnetic field of the neighboring atom, they align. So we have, but overall, there is no magnetic field, because magnetic field here directed this way, here this way, that way, this way, that way, and overall is zero. But we have some areas in which they align. And if you will put this one into the external magnetic field, what will happen? They will align. They all becomes directed, let's say, this way. And this piece of, let's say, iron will act as a magnet. And if we leave it for long enough, in strong enough magnetic field, then it will become permanent magnet. It will keep its magnetic properties. Yes?
What would the segments called again?
Domains. Now, how we can demagnetize permanent magnet? Looking into how we magnetize it now, any ideas how we can demagnetize, make it to stop being a magnet? Two ways. Any ideas? Yes?
Melt it?
Even not necessarily melt, yes, but if you will heat it up, because when you will be heating it up, atoms moving more, and vibrating more, and this alignment will be lost. So yes, heating up.
Wait a long time. Wait a long time.
Too long time. But how you can demagnetize it quickly? One way to heat it up. What another way? What do you think? Drop it. Drop it or heat it, because then you like shake the atoms, and it will not be completely demagnetized, but at least partially. And if you drop it a few times, it will lose its magnetic properties. So if you don't want your magnet to stop being a magnet, don't drop it. So magnetic field created by the moving charges. Either it's a current in the wire, as we seen here, or it's a movement of the electrons in the atom. That's how magnetic field is created. And Earth itself acts as a big magnet. Acts as a big magnet. Okay, so Earth acts as a, we'll start in a second. So Earth acts as a big magnet. It is a big question for which we don't know the answer exactly. We have some ideas how this magnetic field of the Earth is created. But here you can see we have a permanent magnet and we have a compass. If we put small compasses, you see the north-seeking pole, they will be making the magnetic field. They giving you how the lines of magnetic field of the permanent magnet looks like. if we look, we'll come back to that, if you look into the Earth, if we have Earth, as you can see, which magnetic pole is where the geographical North Pole? South Pole. That's why we have of the compass north-seeking pole, north-seeking because it turned into what? North. But why it's attracted there? Because there is magnetic South Pole. And magnetic North Pole is where is the geographical South. They not coincide, they're not at the same point. There is some distance between the geographical pole and magnetic pole. So magnetic pole, field of the Earth is not exactly along the axis of Earth rotation. Not exactly close, but not same. And that's called Earth act as a big magnet. Where compass will be pointed if you will stay exactly on top where is the north magnetic pole. Oh, sorry, south magnetic pole. It will try to turn down. Of course, if it's this, it cannot, so it will at least try to point down, because it will be vertically under you. And we can visualize the magnetic field lines. For example, if you take, I need help of the operator again.
Oh, no, Sam, good.
Okay.
I've had mine.
So you don't take it from the stand, just bring it here and go in here. If you put, so we have here some like magnetic, small magnetic pieces, and if we put it over the top of the magnet, that what happens, they start aligning in the, I will probably put 2 on this one. So as you can see, they align those pieces of, small pieces of iron, they align in exactly the same way. They align in the, showing lines of the magnetic field. Thank you. So, now, important thing, when you will be drawing lines of magnetic field, is same thing as it was with electric. They cannot, on your diagram, they cannot cross or touch each other. Why is that? Why they cannot, let's say, cross? Yes?
Because the magnetic field is always closed.
If you have Tula, you draw it like this. And at this point, at which way, in which direction the compass will be pointing? You don't know. That's why they never has to be on your diagram, never touch or cross. And again, reminding, if in some cases in the question can be small room given for you to draw the line of magnetic field, and if you like you're not good artist and you cannot draw that they don't like touch each other, you write comment that they're not supposed to touch, just my bad drawing skill, I cannot draw any better than that, but they shouldn't touch. Then you will get full mark. But never, they should never touch or cross lines of magnetic field. Now, with the permanent magnet, you know where is the north, where is the south. How we know where is there when we have wire with the current? How we can find direction of the magnetic field? How we can find direction of the magnetic field? And yeah.
How do you make a compass?
Sorry?
How do you make a compass? What's inside it?
How I switch to compass? Sorry. How you make the compass?
Yeah.
You place this small piece of metal that can be magnetized. You put it into the magnetic field and leave it there. You can search this question. Honestly, I don't know the answer.
Iron, they use iron.
Then if you, or you put in strong magnetic field, it becomes magnetized and keep this, and then you just need to make sure that it's put on the needle where it can rotate with a minimal friction, and that's how you got the compass. Yes.
That is a magnet. That is a magnet. That's a lot.
Okay, so this is how we can get magnetic field lines.
Yes.
You see, when we're moving, that's we got magnetic line. This we have magnetic line. And you see, we can lines give us direction in which will be the small compass. The compass will be pointing. That's how we get it. No, it's not correct here because they are touching each other. And now let's see how we can find the direction of magnetic field of the wire. To do that, we need to use the, yes.
Does the lines have to go like through the middle of that?
They should go through the magnet. Yes. Yes.
What if it's like stretched? Like it can't be closed, it's just out to the side. Like for the
When we put two magnets close,
like in that diagram you could have like where it's just perfectly flat here, and then it can't be closed.
sorry, you don't get it. If you mean if you have this and this line not close.
Yeah.
Yeah, of course, one line it's close. It's close, but its radius of the curvature is infinite.
Okay.
Now, here we can use right hand grip rule. This is a wire. Important thing, right hand. Some students mixing their right and left hand and getting things wrong. So when you will be before their assessment task, if you're not sure exactly, put some dot or something on your right hand so you know that that is the right hand.
Is that cheating?
No. So you have wire, vertical, and current. See, why the air, you see electrons moving down. Why we have arrow pointing up?
That's what it comes to.
Because direction of the current from plus to minus, electrons, not in the direction where electrons flows, in the opposite. And I grip this with my right hand with the thumb, giving direction of the current. Current is up, so I grip it. And those fingers give us direction of the magnetic field. And magnetic field, because it's closed, you see it's going around the wire in this direction. It is circle going. So if we look on the diagram,
Which wire do we grab? Which one?
we have wire with the current. We have one wire. Those are lines of magnetic field.
Which way do we grab it? On like the positive
You
side?
grab in the way the thumb pointing to give direction of the current, which current flows.
Oh,
Current flows from plus
to
to
mine.
minus. Yes. So if we
Okay.
Can you explain the thumb thing again? Yeah.
now
Can you explain the thumb thing again?
you have current, wire with the current. Current going up. So you use it right hand. You grip it. And this finger, thumb give direction in which current going.
But doesn't.
And the fingers give you direction of magnetic field. Now, to better understand, let's have a look on this at 90 degrees. Look on this like this. So this is wire with the current. How we can now give direction of the current? With current wire going like this. So current can be out of the page or into the page. How we denote that?
Stick the hole in.
If it is out of the page, this is out of the page, this is will be into the page. Why is that? Why is that?
Like an arrow. X.
Arrow,
X
yes.
marks the spot.
If you have arrow,
Ah.
and when arrow coming towards you, what you see? You see the sharp end. And you need to know that you need to run. If arrow going away from you, what you see? You see the feathers at the end. At the end. That's why this is out of the page, this is into the page. So let's make this current out of the page. So current going that way. So you need to grip it like this. That your thumb going this way. And what will the direction of magnetic field? This way. So lines of magnetic field. So this is a wire, magnetic field is like this. They are around.
Why is it going to the left?
We just did the right thing.
Because that is the direction of how your fingers are going. They're not to the left, it's going around. Huh?
You hold it
So you hold the finger.
Your current is out of the page. You keep your hand in the opposite direction. Current out of the page. This is this way. I'm pointing that way. Why are you pointing in the opposite direction? Yes. Now, this is a good example. Sometimes on the diagram, to place your hand, like while on the diagram, sometimes you will need like to do something like this, which will not be very convenient.
When we need to do that?
How you can sort this problem out? How you can sort? Huh?
Go to the gym.
Turn the page. You can turn the page around.
What do you mean doing that? Why would you?
Because if you have a page and the wire in some way that like this, and current going like this, how you will do? You need to do something like this, which is not very convenient. But if you turn page around, then wire will go that way, and that will be much easier to do. So turn the page to make it convenient for your hand, so you don't need to break your hand.
So if that's going behind the page, you hold it like this, how would you get the lines?
That's how your fingers going.
Why would you hold the
You see your fingers going like this. Now, important thing. What is direction of the magnetic field at the point A? What is direction of magnetic field at the point A? This way. What the direction of the magnetic field at point B? What the direction of magnetic field at point C? This way. Remember, the actual direction at each point is at the tangent to the magnetic field. Makes sense how to apply the right hand grip. It's called right hand grip rule. There are two right hand rules. So when you will be writing, solving problem, and you will have to explain, and you need to write according. If you write only according to right hand rule, this answer will not give you mark. You must right hand grip rule. You don't get write the whole thing. You can write RHGR, right hand grip rule. Because later on we will learn another right hand rule. Right hand slap rule. So don't make them up, you need to use these. Okay, now please, on the compass there are questions which you need to start working on. On the compass there are, it says which pages you need to work on. So exercises from the booklet and not from the booklet. Please start doing it. Please like, subscribe and donate. Support Ukraine and Israel in their fight against terrorist countries and organizations like Russia, Iran and Hamas.